content. Streaming live. Hello, people. So, yes. Oh, it's using that one, not that one. Okay. Video capture device. Okay. That's where you guys are. Right. Okay. That'll be fine. We'll try that. Okay. Right. So I should be on the stream now. And
before you start, I just
yep.
make an announcement. Are we 15? Yeah.
Yep.
Okay. So today we will have Simon talking about networking, and he will cover general topics of networking and socket networking using C++ code examples. So we will not do any Go, but it's kind of equivalent. In Go it's even a little bit simpler. So he will kind of discuss how you do row socket communication using TCP IP. We will talk a little bit about IPv4, and we will see how far we get with the lecture. I will be working on the assignment submission system to make sure that everything is sorted before I actually grade it. So some of you still have issues, some of you forgot to remove the .git thing, for example, like Tomasz. So you have to make an issue for me to manually remove it, because the submission system is closed now, so you cannot resubmit anymore. So if you have some issues with the actual submission, use the issue tracker to tell me. If you have some problems with the verification, some things still don't work, make an issue in the issue tracker. So the discussion board is a little bit cumbersome to work with, like I don't know when you're asking questions and I'm not sure what's sorted, what's not. So let's use the issue tracker, because then it's easier to refer to the issues. Also in the forum, it's not possible for me to refer to a post of somebody else's. It's like a bit of a nightmare with Blackboard. So I cannot say, look at that post, which I already did, right? With the issue tracker, I can see, look at the issue number 41, and then it's like easy linkable. So let's use issue tracker instead. You just register with the prod3 and then put the issues there, yeah?
Where is this issue tracker?
It's on the prod3.imt.hic.no. It's a GitLab setup. Some of you, especially the third years, might already have an account because we are using it internally. So if you go to prod3.imt.hic.no without any /submission, just the root folder, you will have a GitLab. What is it? Like a
sign-in instance of GitLab.
Yeah, so you know GitLab is like GitHub and Bitbucket. It's kind of a third kid on the block in the Git management tools. They had some problems lately because one of the admins kind of did rm space, you know, -rf on the root folder and deleted a bunch of repositories in the official deployment, so they got a bit of a bad publicity, but they're kind of a really cool small team working hard to, you know, to make programmers' life easier, and the tool is quite nice. So yeah, just register, like click on the tab register and register yourself, and then you can go to the IMT2681 project, and then you can issue issues for me. You will only be, I think, able to see that one project, because all the other projects are usually for the members of the group. We're using it for some of the masters and bachelor as well, I think. Yeah. So let's move the discussion of the issues to the issue tracker. So yeah.
How is this platform different from GitHub and Bitbucket? Exactly, like why is that being used instead of GitHub?
This is a local deployment.
This is a local version of the GitLab, so it's our private version, so no one else has access to it. It's not a publicly hosted thing on the internet, it's something we own at the school, so we can...
Yes, so it's physically on a server downstairs.
Yes, exactly. And So with the verification system, they still I'm still not happy with everything. So I'm trying to work out what's not working, but there might be issues that are on your side, right? So if you did something wrong, then the system might not work properly. So we're trying to work out, like, is it the system fault or is it your fault, right? So once I'm kind of happy with the system, then I will do the marking. But in the meantime, you can still update your repo, right? And you can still update your actual deployed system as long as the submission was correctly done. Yeah?
Shouldn't the system be as forgiving as possible?
It should, yeah. So I'm trying to make sure that it is accommodating for the submissions. Like, if the problem is clearly on your side, then the system should not be forgiving, in a sense, right? So if I manually repeat it and it's the same errors, then it doesn't matter if it's the system or it's me, right? I'm trying to avoid running everything manually because we have a lot of students, so trying to automate it. Yeah?
But then it should clearly state that it's your fault.
That's right, exactly. So we're not there yet. That's what I'm saying. So if something doesn't work, it means you're doing something wrong. It means maybe the system is wrong, right? So just issue me an issue in the issue tracker and I will look into it. So once I'm happy with the system, I will announce it on the blackboard and then I will freeze the verification as well. So currently there is no submission happening anymore. Whoever failed to submit, failed with the assignment, but the verification is not frozen yet. So whoever submitted can continue working on it until we kind of are happy that it's done, right? Yeah, that's all. Yeah?
Is there a way for us to check if we submitted correctly? You mentioned something about .git being in some kind of URL that messes things up.
Yeah.
I assume that would be an error that your submission system would give us when we try to hand it in.
Yeah. So if you're verifying your submission and it says the repo doesn't build, then you have to fix it. Like, why it doesn't build? Like somehow it couldn't clone your repo. So in his case, it's because he forgot to remove the .git, right? So if you try to do go get and whatever you submitted and it doesn't work, that means your URL was wrong. So I explained it in the forum. I explained what the exact format for the repo URL should be. I'm not doing anything unusual. I'm just doing go get and the part which is outside of HTTPS. So I'm doing go get github.com and then whatever you submitted. And if you do that command locally with .git, it will not work on your local machine either. Okay, any other questions? Okay, so...
Okay, right, so I'll talk about networking. So you guys are, part of the reason we are doing this cloud course is that we are actually replacing what was a Cisco networking course. Right? So we consider networking very important from a fundamental computer scientist should understand how this computer talks to other computers. Right? Now it used to be we'd also get you to do a whole bunch of physical routing of plugging routers in and taking Ethernet cables and setting up all the cables and doing all of the Cisco router material. Now most of you won't have to do that in your commercial work, but you will have to understand how networks work, and Devon Cloud is a network service thing. Today we'll look and tomorrow we'll look at some of the underlying mechanics that are going on inside the networking part of cloud. So, so in today's lecture we'll talk a bit about general introduction to networking, some tools, some libraries, a little bit of peer-to-peer stuff. Oh, I left the Halo 2 case study in there. We can talk about some of the networking that's done in games and client server and some other libraries, and talk about general network patterns, how things are solved for networking. So, some vocabulary, and I'm interested to see how many of you know these terms currently. So, sockets. 2 people know what a socket is, maybe 2.5. Packets. Okay, headers. Some IP addresses. You've heard of an IP address? Yeah, okay. Protocols, firewalls, octets. Some of you have heard of octets. Right, okay. So there's a bunch of this vocabulary that we'll be going through and we'll be talking about. So sockets are one of the fundamental principles we use for networking. And the idea is that basically we call the thing you plug your power into a power socket. Right? So in English, I would call that the power socket because you plug something into it. Right? Because it's a socket that receives something. And so on computers, the network sockets were the stuff you plug network into to get data to come in. Right? It's also how you send data out. So you send an in and out of sockets. The thing you're sending are packets. So it's packets that go out and out of sockets. The packets have headers, which include IP addresses. So we'll look at those and we'll discuss protocols versus interfaces. We'll discuss a little bit about firewalls, and octets are your data inside your packets. So protocols. So what protocols do you guys know? What network protocols? TCP, yay! What does it stand for? Transmission Control Protocol. And what else? So we go TCP. What else do we know? FTP, File Transfer Protocol, yay! HTTP, which is a hypertext, hypertext transfer protocol. HTTP. UDP?
Yep. Don't remember.
So Universal Datagram Packet, I think. Yeah. So it's UDP. Any other protocols we've heard of?
TCP, the hypertext traffic not control protocol.
Right. Yes, that's a very old protocol. That was one of the first protocols put on the internet because I think it was MIT wanted to have their coffee pot on the internet.
It was published the 1st of April, so yeah, because...
Why would you do it? Yes.
IP?
IP, right? So TCP IP. So IP is Internet Protocol, right? And Transmission Control Protocol is built on top of Internet Protocol. So yes, so we have the ISO model. So how many of you have seen this before? 1, 2, 3, 4.
We've probably all seen it the previous lecture, hopefully.
Aha! Excellent. So you've seen the ISO model. And so we're getting down, so rather than the application layer and your presentation layer, of course, not many networks actually implement all of these layers. You actually tend to just have there's a physical connection. The network and the data link tend to be the same. You have the transport protocol, and then you basically just have the sessions and above, right? They don't actually clearly define all of these parts well. So data tends to just be data, and you have the segments in the transport protocol. And the network, we have our individual packets. So if we have a look at packet structure, so you have some data that I want to send from my computer to your computer. So if we look at building up how do I get my piece of paper with, citytechnic.no, how do I get this over to you? So I have, right, okay, well, I first apply a header to it. In this case, a UDP header would be transport, which would be the source and destination. Right? And that would become the IP data. And I say, it's coming from me, and it's going to you. And then I add the internet routing data with an IP header. And then for the link, I add the frame header and the frame footer. So it builds up this massive overhead of packet. So if I want to send a single byte to you, it's going to take lots of actual data to send that because I wrap it up in so many layers. Right? So one of the things we do when we're looking at sending data is try and work out what's a reasonable amount of data per packet to send. Right? Because you look at the header ratio to the data ratio. So how big your data packet is and how much data you want to send sometimes what you do is you say, well, actually, I won't send this thing as an individual. I'll wait until I've got more things to send. I'll grab them all together and send them as one large packet rather than send you byte at a time, because I don't get to send you single page at a time. I have to wrap this in lots of data, lots of IP addresses and header information and cyclic redundancy checks and a whole bunch of other information just to get it to you. Right? So it's about like, you know, when you're receiving the mail, if I was to send you 100 flash drives, one flash drive at a time, and each flash drive came in a big box as plastic wrap, right? You're going to end up with 100 boxes, each with 100 plastic wrapped. Surely I should just wait until I get all 100 USB drives, put them in one box, and send that to you. Right? So you've got to look out for the headers. Now, an IP header. So we have here we had UDP and TCP IP. Well, we had the IP header. So if we look at that internet link and that IP header, we have the version. We have a bunch of header length, the service type. The total length is a 16-bit integer, right? So the maximum size. What's the maximum size this packet can be if it's got a 16-bit integer as its total length? What's an 8-bit integer? How big is an 8-bit integer?
The size could be like 65,000 bytes.
65,000 bytes would be the absolute maximum size. The problem with making a data packet that large would be you're likely to lose bits of it, right, in your transmission. So usually we don't build ones that big, but that would be the maximum packet size. Is 65,000. What is 65 something? Is something 364 or something? But yeah, so it's a 16-bit integer.
65,536.
536. Yeah. So that's the maximum size. So you can look at these and say, okay, so there's version number, which is 4 bytes, a header length, which is 4 bytes, which is how big this header is. The service type, what kind of packet it is, total length, identification, there are flags, there is a fragment offset, there's the TTL, there's which protocol we're using, the header checksum, the source address, the destination address, and options and padding, right? So we've got this IP header, this Internet Protocol header. Now, this is IP rather than TCP IP. So as Internet Protocol, this just has source and destination. It doesn't have information about what individual packet this is in a sequence of packets. It just says, here's enough information to get this letter to its destination. If that letter doesn't arrive, you know, you don't know. It's just saying, hey, this is a packet. This is where it's coming from. This is where it's going to. It has the header checksum up here. The nice thing about that is it says, you know, it gives you a way of checking that nothing was edited in this header after I created it. Right? So if you get a bit flip or a bit error in the header which changed the destination, your header checksum says, oh, no, that doesn't add up anymore. I've had a bit flip, because this is physical hardware that it travels across, which occasionally it will bit flip. And so you can just drop the packet and say, no, it's the destination address or something is wrong because the checksum doesn't work. So you've done checksums? You know what a checksum is? Yeah, cool. And so it has some options and some headings. So this is, as you see, this is we've got 4 bytes, and there are 4 bytes per line, and there are 6 lines, so 24 bytes. So if I want to send you 1 byte of data, right? If I wanted to send you a character, right? The character S, and that's 1 byte. I'm going to send you the character S. I've got 24 just in the IP header to sit on top of that. So to send you 1 byte, I'm already sending you 25, just to get that 1 byte across. Then you have a TCP header, which has a similar source port and destination port, because the IP is just sending it to a machine, right? So I send it to you. TCP adds the ability to say, well, actually, instead of just sending it to you, I have a protocol that says, I sent it to you, and you should file it like this, right? So, for example, I say, you're a web server, I'm asking for port 80. Okay, magic. So I'm asking for port 80, right? So TCP adds additional protocols on top of the IP, right? So the IP protocol gets it between you and me, but then TCP says, you might want to file this in a particular way. So I give you 2 bytes, right? So there's the word octet. You'll see the word octet there, which is the 8 bits for a byte. They're called octets because we're not talking memory. We're not talking the RAM memory. We're talking about networking protocols. So they use a different word for it, octet. But it's 8, right? So, which is the same as a byte, but we're talking network protocols. So we give you 2 of those, so 16-bit for the source port and 16-bit for the destination port. Critically, it gives you a sequence number. Right? Now, if you're using UDP, you only get this stuff, right? You get source and destination, you don't get anything else. So anything else you have to put in the actual data. Here, TCP says, here's a sequence number. What that means is if your packet gets lost in the mail, right? If I'm going to send you your IKEA furniture 1 box at a time, I'll label those packet 1 of 5, packet 2 of 5, packet 3 of 5, packet 4 of 5, packet 5 of 5. So if you receive these packets through the mail and you get 1, 2, 4 and 5, you ring up IKEA and say, wait a minute, I'm missing packet 3. I ordered a whole bookcase, not just the frame, right? And they send you all the connecting bits that actually give you shelves, right? So you ring them back and say, I'm missing this sequence numbered packet. Now in TCP protocol, what happens is you actually build up your file by saying, okay, I got 1, 2, didn't give me 3, I've got 4 and 5. I'll say, okay, well, I'll wait now. Give me 3, please. Right? And I won't give it to the application. I won't finish loading the network packet and building it until after I've got all of the things I'm supposed to get. Then I put it together and hand it forward. Right? So I don't hand a file that has 1, 2, 4, 5 and say, there you go, and hand that off to the application that's trying to do a TCP communication. It waits until it gets everything. Waiting until you get everything can be a problem, right? Because, you know, you lose a packet and suddenly you've got another whole round time ping. So I've got to send a message to the server has to process that message, work out which packet it missed, resend that packet, and that's got to come back, right? So if you're using if there is packet loss in your network, say you're doing a wireless network and there's a bit of noise, and so occasionally packets get lost, TCP, everything slows down because it waits until it gets every single packet back, right? And if it gets one out of sequence, it waits and tries to fill up with the older packets and asks for re-acknowledgements. So this is what this acknowledgement number, which is a 4-byte number, so 4-octet number, and that is the sending and receiving acknowledgements, right? So you'll sometimes, there's some network humor on the internet where you have ACK and NACK, right? So ACK is for acknowledged, I've received that piece of information, and NACK is for not acknowledged. So when you sent me something that I can go NACK and say, no, that wasn't what I was expecting, right? And so you'll see some humor where people talk about responding with NACK when asked to do the dishes. NACK. You sent me a message, it wasn't the one I was wanting. So not acknowledged. So yeah, and you get those kind of acknowledgement sequences. And where that gets interesting, and one of the network challenges we have, is handshaking to set up a connection. Right? So, and the classic example we use of this is in combat. Right? So if I have set up my forces on either side of a valley, right? And the enemy is in the middle of the valley. And I want to say attack at dawn. So I send a messenger from here to the army on the other side of the hill and say, right, we're going to attack at dawn. But he has to run through the valley where all my enemies are. So how do I know if he's got there, and how do I know if the other group are going to send their forces at dawn? So the guy runs across there, tells them we're going to attack at dawn. They say, great, we're going to attack at dawn, and they send him back so that he can tell me that they got that message. So he then runs back across the valley through all the enemies and gets back to me, and I go, aha, you received, so you got back here. So I now know that they know we're going to attack at dawn. But you don't know on the other side of the valley that I know that you're going to attack at dawn. So I have to send my guy back again to say, right, tell them that I got that message. And he runs back across the valley while being shot at, gets to you and says, right, they now know that you know that we're going to attack at dawn. And so how many times do I need to do that before we all know that we're going to attack at dawn? Right? Now, so that is the classic handshaking problem of how, if I send you something, how do I know that how do I know that you know that I know you got it? Right? Because I can't, if I just send the guy out, I can't possibly attack at dawn, right? Because he might have been killed. If I get them back, you can't attack at dawn because you don't know that I know that you're going to attack at dawn. So I certainly have to send them back to you.
Well, why do the forces on the other side need to know that the first group of forces got the message?
Because if I'm sitting here saying, right, I'm going to attack at dawn, I've sent my messenger out, but I don't want to attack unless I know you're going to attack. Right? And so I want to hear back from you. Which means I'm not going to attack until I hear back from you. And then you're sitting there thinking, well, I've sent him back, but I don't know if he's got back across. So you're waiting for him to come back to you. So you've got to cross the valley 3 times just to try and get this message. Now there's another way of doing it, whereas you flood the valley. So what I do is I just flood with messages, right? And just send hundreds of messages at you, and then you send, everyone you get, you send one back to me, right? And as soon as I get that message back, I stop sending, which means you hear messages coming all the time, and when they stop, you go, oh, okay, we've stopped now, so that's good. But then you don't know whether the network went down, so handshaking. So this is what this acknowledgement set is, right? So the acknowledgement there is to do the handshaking back and forth in the protocol. We have some data offset, we have some received information, and then we have individual flags, which are individual bits that are set. We have the window size, which is to do with the sequence number of how big your window is when you ask to resend things, right? So there's a whole protocol around how big your window is when you're asking for information back. We have a checksum in here, again another one just to check which bits are broken. And an urgent pointer, right, which is supposed to tell your routers how important this particular TCP packet is, right? One of the problems with allowing protocols an urgent flag is that you might have noticed this sometimes on emails. There are some people who just always flag their emails as urgent all the time, just because everything I say is massively important, so you should just know it all. So unfortunately, user-controlled importance is not necessarily a great way of dealing with managing data. And yeah, then we have the options of the data offsets greater than 5, so there's padding with 0 bytes if necessary. So so then after TCP, you get this large data block, right, which has got the IP header in it, right? So inside that data block is this thing, is inside that options and the data block later, right? So you get this whole massive packet. So we've got another 16 bits on the TCP, well, starting from 20 bits rather at the TCP, and with some options up to 160 bits of so 24 bytes, no 20 bytes to here, and then some additional options bytes. And so you've got 24 from the IP header and another at least 20 from the TCP header. So now my 1 byte is taking 45 bytes to send you. Okay? So this is getting a pretty bad ratio if I want to send you a single byte of data. So I want to send something at least reasonably large. Okay, so if you want to see stuff happening, there are tools like Wireshark, which I was just setting up on this machine, seeing I hadn't used it before on this machine, which is why it's doing that. And I can go next. Finish. No, I want to manually group data. Finish. Yep. So so Wireshark, because I hadn't run it for a few months, did an update. So yeah. So Wireshark allows you to look at what packets are going in and out of your computer. Right. So this is quite useful just to see what kind of packet information is heading around. Right. So and you can see if I can make this bigger. Nope, I can't make that bigger. So so all interfaces shown. So it's enter capture filter. So I can so I've got no interfaces shown because I haven't attached my with the new update. So file open. Where has it gone? So traffic. Enable promiscuous on all interfaces, manage interfaces, so pipes, remote interfaces, local interfaces. Oh, it's not seeing my card. Arg. That's why, so having done an update, it's now, okay. Well, we'll come back, maybe we'll do Wireshark tomorrow, so we'll come back to that. We've got plenty to talk about. I'll show you some code first. So, rather than kind of inspecting packets, which we'll do tomorrow, we can have a look at SFML and STL, right? So these are, so networking in C is really, really annoying, right? Because low level socket creation and manipulation is really nasty, right? Even with libraries like SFML and STL, it still is a bit of a hassle, right? So what we have, and I'll show you the STL net because that's the examples I have. Some of our students have used SFML and used networking there, but if we take you to some STL code, so this is a client code, and as you can see here, I have no, you can find it. I know you can find it. You're finding it. Okay. I'm not sure why it's complaining about that. I'll see if I can make this slightly larger. Where's the zoom feature? Font size. There it is. Is that big enough? Or do I need to go 200? I'll go 200. That'll be large enough. Okay, so as you can see here, why is that not working? Okay. So as you can see here, I'm doing a standard C++ kind of operation, standard IO, strings, and I have lists and strings. So, and then I use STL, which is the general framework, and STL net. This is actually a piece of client code, and I also have over here a piece of UDP server code. Now this is UDP, so it's a data packet, datagram packet, and so it only has source and destination, and so this is a simple server where I create an STL net. I do a UDP socket and a UDP packet. Right, so these both are defined in STL net, right? So these are type def in here, and so I create these, and then I do an STL init, and if the and this is error checking, so I initialize STL net here as STL net init, so this initializes the two libraries. I then do an open a socket where I say, right, okay, so STLnet underscore UDP open 8880. Right, so in this case, it is I am on this machine opening up a port 8880, and I'll be listening to that port. Right, so whatever the IP address of this machine is, anybody who tries to connect to me on 8880 I will listen to, and I will give out and open that socket so that I can communicate. I allocate some space for a packet, so I allocate 512 bytes for a packet to receive a block of information on that port, and then I enter into a main loop, and in my main loop I do a blocking wait. This with a massive comment underneath it, STLnet UDP receive, written RECV because they couldn't be bothered writing the word receive. It's a bit sort of silly, but so I do a UD packet receive, and I say, right, that was the port, that's the network port it's coming in on, and that's the packet, right? So I have the socket, so SD is the socket descriptor, and P is the packet I'm getting in. I then can print out the packet, and I have P channel, P data, and I can give you P data 1, P data 0, P data 1, P data 2, and P data 3. So I can print out some information, and those have been turned into 32-bit integers, and then I can show you the length, the maximum length, the status information, and the address host information, and otherwise I've got an STL delay 20. So what this is set up to do is my receiver will actually wait 20 milliseconds before testing. Otherwise it would sit here spinning my CPU going data packet, data packet, data packet, asking constantly, polling constantly, right? Because it'll kind of spin and ask. Otherwise I do this delay and it waits a little bit and it comes back and then just exit, right? So this is a server which is just sitting there waiting for people to send in information. It's not responding to anything, it's just waiting, listening. Right? So if I run that server, and I have the code in here, so if I run that server, I spin it up, and it goes to there. Oh, I should close down the currently running one, otherwise it won't like it. So I spin that one up, and I go yes, and my firewall goes, oh, do you want, because it's asked to open a packet, Windows goes, wait a minute, you've asked to open a socket with a port number. And so it says, are you sure you want this person to be allowed to access the network? And I go allow access. So, and once it wakes up, and Windows will hit yes. So I then have nothing happening, right? So this is now a server on port 8888, just waiting for stuff to happen. And so that's me setting up something that's now listening. Right? It's just sitting there listening on port 888. If I ping, I think if I go to here and go escape, I think if I actually haven't tried this, we'll just see if this works. So it's home is 127.127.0.0.1 is home, and there's nothing there at the moment. And if I put in port 8880, there should be nothing there, but did my thing receive? Ah, no, it wasn't listening, didn't come in the right format. So I don't think my browser will attach to 127.0.0.1. I don't know what happens when I try and do that from the browser.
Yeah, it's on port.
Yeah, I'm not sure what happened, but luckily I don't have to use my browser to do that. I actually have code, in this case my UDP client code. So with the client code, now I've actually got this code which I can share with you. Yep.
Ping it through command?
I can try and ping it through command line. So
you open the port 8880 on TCP or on UDP?
UDP.
So you can't.
So I'd need to, yeah, because TCP. So
ping goes over ICMP protocol, and then the normal browser goes over TCP. TCP, so he can't actually check.
Because I've set up a
easily
UDP port.
Yeah.
It's saying I want UDP packets, not TCP packets. Right?
Can you use Postman?
No, Postman either. You need to use like a netcat or something that can generate UDP packets. So
Yeah.
Postman also operates on TCP packets.
Do I have netcat on here? No, I don't have it at command line anyway. So I've got my own program to ping my server. And if we have a look, so this program actually does a whole bunch of stuff, and we'll get to that. But it also does, I've got some TCP stuff which we'll get to, which has, you can see here, this TCP open bit, right? So I also have some TCP connection material here. But if we go down to this bit down here, where we actually connect, I create a default server name. So it's set up to be 127.0.0.1. So this is localhost, right? This is pointing to myself. And port 8888, which is the port I had set up on my server, and port 8881 as me as a client, right? So I've just set that up as if it wants to talk to me, I can open up that. And if we scroll down here, I do some stuff on initialization. I then init STL, and then I init STLnet. So those are the two standard initialize your libraries bits of code. And then this is my TCP function call, and I'll show you how that works when we start talking about TCP. But and this is actually an example of how to resolve host with TCP and get something from port 80. But here, this is the bit that's interesting that I'm showing you, is this UDP socket is STLnet UDP open default client port. So I open up on 8881, and then I do STL UDP open 0, so it opens a socket on a random port, just to see that that works. And then I resolve host with the server address, the server name, and the port number. All right, so I ask STLnet to go and say, does that exist? If it doesn't exist, say, I couldn't find that server for you. If it does exist, I can continue. And then I allocate some memory, like I did before, to receive information from the network, and I go into a loop. In this case, I'm doing some weird stuff here, which I'll explain, which is I start an interactive mode, and I try and fill a buffer. So if I build and run this, so I build and run this code, and it's building. It's telling me the scanf is a deprecated function, so it's naughty and I shouldn't use it. Okay, so it asks me again, do I want to allow access? And I go, yes, allow access. Now wait for it. Okay, so now I have, and you can see up here, well, you can barely see, but so if I look here, I've got information about memory and network packets and CPU utilization running on, because I've got diagnostic tools running. If I go into here and I type in the word Simon, I send that, and if we have a look at my server received a UDP packet which says incoming packet, channel -1, data Simon, XY large strange number, XY small short strange number, then the number 23, the number 12, length 24, maximum length 512, status 24, and address blah. Okay, so I'm making it write out some information. So what I was writing out was print the packet data, right? So this is taking the packet data, set. That's in the client side, and the server side. What I was printing out was cast the pointer data, the packet data 1, into a 32-bit unsigned integer, because it's just packet data. So when I look at my packet data here and say, what is this 6F6D 6953 strange thing going on. What is that? Can you guys recognize any of those numbers? 6F6D 6953 and then 6E. Do any of you recognize any of those? Okay, so let's see if I go to view, properties, so font, width, height, font. Can I make it big? Okay. It's a little bit better. Maybe not good enough, but it's a wee bit bigger. Let's see if I can do that again. Let's see if I can find a bigger font.
Use magnifying glass.
Console 72. Okay, right. There we go. That's a bit bigger. That's now my whole screen. So, so do you recognize 6F6D6953? Right, because if you ever look, that's what I've done here in the code, is I've just turned my data 0 into an unsigned integer. Do any of you recognize what might be? Can any of you kind of work out where those numbers are coming from? Do you know what 53 is? Do you know what 69 is? Okay. Are there any? Can you think of something that might be working? Ah, the hex values of ASCII characters. So what is 53 in ASCII? ASCII codes, table 53 is, ASCII 53 is the number 5. So so that's the number 5, and 6F is, oh wow, 53, no, 53 is 53 in ASCII S. There we go. The hex value of S is 53. So S and then 69 is lowercase I. So 53, 69, 6D will be M, and 6F is 0, and 6E is N.
Why is it backwards?
Aha! Exactly. It's backwards because of Indians.
What?
Indians, yes, Indians, like cowboys and Indians. So Indians are to do with how do you decide which is the most significant end of a piece of information, right? So you can have big Indian or little Indian, right? And that determines on which number you send first, right? So in my data packet, when I send you a data packet, you have to know which order I will unpack the data to send the data correctly, right? Because here it sent Simon in as a string, and it unpacked it from the first letter into this char. When it did char of that 4 bytes, right, it took the first 4 bytes that it got, which was the name SIMON, and it's assuming little Indian. It's assuming the smallest bit is first. And so when it built it back up, when I print it out, it looks like a number, hex number, that is got S as the very first number, the smallest bit. Because it didn't take it and say, oh, that will be in big endian format. It'll have the biggest number first. It's little endian format saying it will have the littlest number first.
What do you mean the biggest and littlest numbers? Like the values of the characters?
Positional information. So you guys did, so my daughter at the age of 8 has been doing the tens column, the ones column, the tens column, the hundreds column, the thousands column. You guys all used to that column-based system? Well, so if I write down a number, and we'll go over to the whiteboard. So do that. If I'm over here and I write down a number, and I write down, I don't even know if it's looking at me, 1,000, right? You guys are used to teaching this as is 1 in the thousands column, right? Now, if I'm going to send you that one number at a time, do I send you the 1 and then send you a 0 and then another 0 and then another 0, and each time you have to take that number and multiply it by 10, right? Because you've processed strings like this, yes? Where if I send you the number 1 and then I send you the number 0, you're going to have to say, oh, that number was times 10 plus whatever number this was. If I send you another number, times 10 plus whatever number this is. And then I send you this number, so if it's 101, it times 10 plus 1, right? Now, if on the other hand, I was to send you something that broke, if I was to send you in little endian, so this would be sending you big endian, the biggest number first. Little endian, I'd send you this number and say, right, I give you 1, and then, so I give you that one, and say, nothing in the ones column, nothing in the tens column, nothing in the thousand column, and nothing in the 100 column, 1 in the thousands column. So I'd send you that, and then send it this order, saying from the smallest number first until I run out of numbers to send you. Right? And so that would be little endian, because I send you the least significant bit first. And this would be big endian, because I sent you the most significant piece of information first, the 1,000. And then I'll send you the smaller and smaller bits. Right? So knowing which order you receive that in is critical for unpacking your network data. Right? So anytime you're sending network data, if you unpack it in a different way you packed it up, you might get this little endian problem. So when you write date, if you're writing date in a file, right? If you want it to sort properly, today's date is 2017 09/26.
I think so.
26? Yeah, 26? 25.
25, yeah.
That's how you write today's date, because that will sort properly. If you write it the other way down, the 25th of the 9th, 2017, when I try and sort this, what happens? I get everything that happened on the 25th of any year, of any month, all sorted together, as if it's the fact that it's the 25th day that's the most important piece of information. So I sort it on little endian sorting, and that's stupidness, because today's date's not, like grouping them by the 25ths is insensible. Right? But that's what will happen when you do that, right? I'm sure you've had that happen. Yep. Blackboard, massively annoying, because when you create group assignments, and it automatically creates the numbers for group assignments, it creates group 1, group 10, group 11, group 12, then group 2, 3, 4. Because even if you tell it to create 20 groups, it doesn't have a leading 0, and so the groups are all sorted by the first digit, and so you get them sorted like that. 5, 6, 7, 8, 9. That's annoying, right? Because that's the wrong way to sort that list. Americans do what is generally universally considered an abomination against all ordering, which is middle endian. Right? And so you put the date in the middle.
The month.
The month in the middle, and then the day, and then the year. Middle endian is really hard to unpack, right? Because, and I think IBM had a Middle Indian system as well at some stage. It was using Middle Indian for sending data. Which is going, why did you do that? So this idea of how you pack data into bytes. When I pack it as a string, it packs it as Simon. And then when I tell it take this and turn it into a number, it goes, oh, you would have packed it Little Indian. So this will be the lowest part of the number, and this will be the highest part of the number, which is why you got the 53, 69, 60, or 6 E was it? I think. Oh, 6D, 6F, 6E. Right? So there's actually 6E. If you have a look on the screen, if we, I'll go back. If you have a look, it actually is in the next integer. Move me over there. So he made me bigger and he put me over there. Right. So here, this just casting data, right? So this would be, this is actually data. So if I said this was data first, and this would be second. And here I'd be looking at this X data 2. Now, you guys know how arrays work? You remember how arrays work from last year?
Arrays. Yeah.
Arrays, yeah? So when I cast something to a pointer to 32-bit integers, that means this offset looks down 32 bytes at a time. Yep, you're happy with that? That, you know, it's an array, and so it jumps 32 bytes at a time. So if you have a look at my client code, if I look at the client code, where you see me here setting that to being a number, what number would we like to send here? Pick a number. I'll delete this and change it to a number.
58.
58. Let's put 58 there, and I'll save that. I'll kill these. I'll just kill the client, and then, so if I build that, now if we then fill this buffer and we say, let's say, so we now recognize that S was 53. So if I go S, let's just make it too big, right? And if I do that, and I jump over to my server, it's now received S. The data was 53, 53, 53, 53, 53, 53, 53, 53. That was the first 8. There's your 58, right? Because you asked me to send 58. I've now sent 58. And 12 was my Y. Now, if I go back to here, see data packet 8 is 58, but I've got 8, 9, 10, and 11, because this is big endian. So if I set this one to being 1, right, that will send the high end bit in byte through. So if I save that, and now you'll get the standard problem if you don't save it, I'll get rid of that one, and I'll go back to this one, wait, back here, build. So if you don't quit out of your program, it'll say you can't make the program because the program's already running. You guys have hopefully had that. And so if I go let's do 4 S's and 4 little i's. Okay? So what do you think was sent?
I was just wondering, the packets convert the strings to hex ASCII values?
So what happens is your data is always sent as bytes. Right? So whatever you put in here, you send as bytes. Right? And so what happens is that on the other end, I get a bunch of bytes. Now, as you can see, if I put an i's, and by adding that 1 there, I've now got 16 million 7777274, because I added 1 at the big endian at the top end. Right? But no, the reason why is that everything gets sent as bytes, and so you have to take your packet, and if you convert everything to char, that's what it looks like, right? But because I had null terminated, so incoming packet, the data was SSSI because it was null terminated, right? I think if I scroll up, yep. So you see that the data there actually that colon is caused by the 58 that you asked me to send. I think that's what's causing the colon there, because yes, it's sending and it's trying to print out the packet. Let's see if I get that. If I go in here and instead of sending a 0, I send a 58 or 59 and a 60 and a 1 and a 1.
That's a colon, yeah.
So 58 is a colon because I packed data and then I didn't have a 0 terminated string. If I send data 0 and I'm saying I want a string, if I hit 0 when I'm trying to print a string, I'll end with printing the string. Yeah?
So, is it possible to read like the hex code like that? If you send Simon without knowing it was Simon,
Yep.
in hex, would you be able to read it?
I can read ASCII, so yes, I could just read the data.
How do you know the difference between 58 and 5 and 8?
Because you get the raw, it's raw binary, right? So you just have to cut it at the right point. And so if you cut it every 8 characters, so into hex, right? So you cut every byte, which is going to be a number between 0 and F, right? So you take every byte and you turn it into a 0 to F, and you read it out as, well, every byte, and you treat as hex as being, you know, 58. That's actually not 58. That is a sequence of 0, 0, 1, 1. So it's 0, 0, 1, 1. No, those are numbers. So 69, if I've got to kind of remember this correctly. I don't have to remember it. I can go to my table that I have here and go control. So if you actually look at these, if you ever look at space, for example, that is actually 0, 0, 1, 0, 0, 0, 0. So that sequence of bits, if you turned it in ASCII, would be space. If you turn it into if you try and turn it into a number, if you try and interpret it as a number, is the number 32 in a decimal, and it's 20 in hex because it's 0, 0, 1, 0. The first byte is 2. The next byte 0.
How can you tell the difference between, for example, an integer number and a chart?
You can't. You can't. You just have to know what they sent you. Right? And that's why we have so much networking protocol on the top of it to say, what exactly are you trying to send? Right? Because I need to unpack it, A, in the order you sent it, and into the kinds of things that you need me to convert it back into. Right? So if it's integers, I need to know it's int. If it's string, I need to know it was a string. Right? So that's why we put so much header information around, because you don't know. Right? Now you can decide to send everything as a string, so you send your numbers as strings, but that means you send the ASCII 5 and the ASCII 3 to get the number 53, right? Which is a bit stupid because you're sending 4 times as much data as you need to send the number 53. You're sending 2 characters, right? So you're sending you're sending 2 bytes instead of a single 4-bit number, right? So you can pack things much, much tighter. And so if you have a look here, when I was actually doing this code, here these are U8 integers, right? So I'm creating an integer here into 4 bits, and here on the server side, I'm turning it back with uint32. I could do uint16 or uint8. If I did uint8, I'd get the individual characters out. But uint 32 grabs it as a whole 32-bit integer. Alright, which is here I print out %x is the hexadecimal value, d is the digital value, right? So the decimal value of whatever I converted. Okay, so this is an example of me sending information back and forth and being able to kind of have to understand how is that data being sent. And in my sending packet, I really am literally sending bytes. If I want to change packet, actually, so if I save that and send 58, 59, 60, and I stop my client and I rerun my client. Dun, dun, dun. So, what will that send after my packet? So 58, so now I have to make sure my string is long enough so that it gets to that data. So Simon space MCC A. Right, so what should it print out?
Colon and a semicolon.
A colon and a semicolon. Let's go and have a look at what it did.
It was 53 that before.
Yep, so let's see. So where is... Okay, why did it only give me the MCC bit without the Simon space? The space seems to, but it seems to have lost. Right. Ah, it sent 2 packets. So yes, because I actually have. Yep. Scroll it up. There's the word Simon, and then the word McCallum, because I actually split on my sending around the space, because if you have a look at my client code, I actually have a yeah, so it actually split on space when it sent the packet. This is the yeah, so the server side, it receives it and splits it up on, yeah. So what that came across as 2 packets. So let's try this again with aha. So MMMM and then colon, semicolon, lesson symbol, spade, and then gender, male gender, right? Because those were the numbers that I was sending, right? And they happen to be the those ASCII values, right? So if you try and convert ASCII, if you try and convert integer numbers into ASCII, you get weird stuff like that. So you guys may have seen this from network packets, where you look at network packets, it's full of random crazy stuff, right? But actually it could be a string, or it could be your health, or your hit points, or your XY position, just written as a number that you're trying to turn into strings, right? So this is kind of the fundamental part of understanding networks, is you're sending data over those networks. Right, okay, so we're going to have a 10-minute break and come back in 10 minutes, give you guys a walk around, then come back and we'll keep talking about networks, because I've still got a lot to cover today and some more tomorrow. So come back in 10 minutes.
A funny networking story. In I don't remember which country it was in Africa. It was a very bad one, I think, in South Africa. And the internet speed was so bad that they strapped a
SD card.
Yeah, SD card to a carrier pigeon and sent it, and it got there before they could download 4 gigabytes.
Yes, yeah, and in fact, it's still, if you strap micro SD cards to pigeons, you can actually get much faster data network than even than fiber, right? So because if you put like 256 gig SD cards,
400 now with SanDisk.
right? Well, yeah, you can okay, you can do 400 SD cards, but if you get 256 gig SD cards, right, or even 64 gig SD cards, pretty cheap. You strap 5 of those to a pigeon, right?
It's a lot better.
Transferring 300 gig of data takes a while. Just take a while, and it's also more secure because you're not sending it over the network, because you know they've got to shoot the pigeon.
Yeah.
With hundreds and thousands of other pigeons.
All the other pigeons.
Courier pigeons are trained so that they fly to the same point.
Fairly uniformly. Okay, so question? Nope. Okay. So you're just
Right.
just listening into this. Yeah.
I was thinking about doing a prototyping session with the first years so that they could get into their assignment.
Right.
So I was just wondering, when do they have a time slot that fits during the week? Like, it's not Friday
They
evening?
probably do. So that's
Because I was originally planning to do it yesterday, but due to having way too much to do, it didn't quite work out.
Yeah.
I have a question.
yes. What's your question now?
You're using STL
Yes.
to open the socket.
Yep.
Have you tried using like an operating system
Windows sockets.
or Linux?
Yeah, I've done Windows.
Is it easier?
Much harder because basically STL wraps up all of the socket communication inside this.
You have to be more specific when you talk directly to the OS.
Yes. Yeah, you have to add more parameters, and so if we have there are, no point in redirect. So that was actually my next slide. Was there's
STL
STL and SFML.
supports Linux, Mac,
Yes. Yep.
Windows.
Yep.
Yeah, with the same.
It's exactly the same. That's one of the nice things about it is because it's cross-platform. It'll run on Linux and it'll run on Windows and it'll run on Mac, and you just get to use the same network code and it will just run. And you don't need to do any other part of STL if you just want to use STL and STLNet. It's just a C++ library, so it will work with most other implementations. If you want to do sockets directly, you then would have to know, you have to ask which operating system you're on, so your code then has to check is it's Linux or Windows or Mac, and then depending on which operating system it's on, it then has to open up operating system specific sockets and do the
Implemented.
which is a different implementation between the different systems, and then you have to pack the data differently, and you have to give it different headers, and you have different endians, and it's all.
And you also probably have to bind to the specific libraries in the specific OS
Yes. Yeah.
during compile time. But
Yes.
are there any reason to write operating specific code ever?
Not anymore. I mean, so so what I was going to talk about, so there 0NQ is another example of a very very lightweight networking socket communication tool.
Yeah,
right?
because maybe it uses more memory if you.
A little bit, yeah. But the difference is because the physical distance is our limiting factor. Right. So one of the neat things about you guys have is to increase the speed of things, you have to move them closer together. Right. And so that's why cache has moved. You've got so much cache on the CPU, so it's really close because the physical distance out to RAM is a long way. Right? So it's all the way over there, right? So that takes a long time to get there and get back at the third of the speed of light that electricity is traveling. And so there's a maximum speed you can communicate with RAM.
It's just a third.
Yeah, the electricity is the third of the speed of light. So yeah, that's why optical computers would go 3 times faster.
Yeah.
Because you'd have optic communication rather.
Theoretically.
Yes, yeah, but they're actually building those. They're building ones with optical buses to try and lose that distance. Yeah, so
Copper.
they're non-copper. It's just
Is
all
it more expensive?
yes.
It sounds expensive.
It's much more expensive. Well, it's more the converters are quite expensive, right? So you've got to have light emitters to emit the signal down the optic fibre cable. Because you've got your glass fibers are cheap, right? So the glass cables are cheap.
You don't have to convert electricity because it's already electricity.
So you have to
Coming into
convert the electrical signal into photons. So you have to have basically an LED to shine the light down the photons to travel down the.
But in a copper machine, you
Yep.
don't have to convert because you already have it in the right format, sort of.
Yes.
Like the energy is in the right
Yes,
format.
it's already electrical. So yes, so you don't have
But
any
you have to
conversions and
change the voltage, of course.
yeah,
But
yeah.
it's
So
less.
it's cheaper.
Yeah, it's cheap.
It's cheaper and it's copper.
I was wondering, about networking is hard. How much of networking is hard because of security reasons?
Not a lot, really. Networking is networking is hard. It's not really security that makes the first bit of networking hard. So you just getting things to work well together takes people time because of the Indians and knowing where things are and the port numbers and all those. So once you've sorted all that out, then security makes it hard. So the next bit of security that makes it hard is when we're going to talk about firewalls and network protocols and stuff, and having firewalls stopping you communicating. That makes networking even harder in a highly secure environment. So,
I think something that makes it really hard is that there is no type safety on the net. So there's just strings.
Well,
So
no, there's just
it
bits.
all-
There's
it's
just
all-
bits.
Yeah, it's nothing is explicit. There is only implicit information, so you have to interpret everything.
Yep.
But when you're inside your C++ environment, everything is type safe.
Safe, and you've got more security. Yep. Okay, so right, I see people are coming back into the room. Yay, people back in the room! Excellent. Yay, internet people. Okay, so we've been looking at code, and tomorrow we can look at some more code. I've got some more actual discussion around networking. So if we have a look at other libraries, so that was the STL, SF, and SFML is similar with network sockets. Here you can go to the STL and look at the network sockets I was using. There are lots of libraries. I don't suggest reinventing the wheel and going down to actually socket libraries in Windows and socket libraries in Linux, because if you want to do operating system level sockets, you have to open those up, which means you have to check which operating system you're on, and then bind to those specific networking libraries, and then bind those specific sockets for each operating system your system might work on, right? Whereas with STL or SFML or any of the other libraries, you get kind of that for free. And we would suggest find a good library, find one you like, and then use that. Okay, so interfaces versus protocols. Do you guys know what the difference between an interface and a protocol is? What's a protocol? You just mentioned some internet protocols earlier. What's a protocol?
Certain ways to handle certain data.
It's a way to handle data. What's an interface?
A way to tell other protocols how to handle data.
Nope. So, an API. What's an API?
An interface?
Right. Yes. What's the difference between...
That's the interface in the name.
Yes. What's the difference between an API and a protocol?
Is the interface higher level?
I would usually go the other way, right? An interface you might consider a specific instance of a protocol, right? So a protocol describes the way in which we discuss things, right? An interface is one specific instance of this is how you interface with this particular thing, right? So, so an interface might be a high score list or a leaderboard would be an interface. So my API, right? If I have an API, I have you send me this piece of information and I will store it for you, right? That could be an API. Or you ask for this, I give it back. A protocol is, this is the structure by which you will send data. So it's at that higher level. So the TCP, the protocol of TCP, structures how you send. It doesn't care what you're sending within the data, right? It's not an interface, it's a protocol. It's a description of how to communicate, rather than an individual response to a communication. So let's draw this into the real world. A protocol might be how you you get a protocol around how you greet somebody, right? Which are the protocols of you know, I'm supposed to like nod, and I'm supposed to give deference to people higher status than me, right? An interface might be the where you actually have someone using a specific language and saying, right, you're supposed to say this. If you ask me which way to the toilet, then I will give you this information back. Right? That's an interface. I'm a robot that listens to text. Now my protocol is listen to something, reply with something. My interface is I'm waiting for instructions on you to ask me where the toilet is, and when you get that right, I will give you back the specific information. Right? So an interface has very specific things you will do. The protocol is the structure by which you would do things. Right? So maybe you could think of a protocol as a communication protocol, whereas in Norway, in New Zealand, if someone's speaking, they have the floor, and when they stop speaking, you can start speaking. Right? That's a protocol. Right? In Norway, the protocol is this whole one finger, two finger meeting etiquette thing that you guys do. Right? Which means whenever I'm talking, like when I'm in a meeting and someone else stops talking, as a New Zealander, my protocol says I can start talking. Right? So I'm apparently very rude because I don't wait for people to have their turn. I just start speaking because that's the protocol we have in New Zealand. Right? That's the communication protocol. An interface would be English, would be an interface. Right? So I interface in English is my interface. My communication protocol is my culture. Right? Do you understand the difference? Like, can you see the difference between those two? So one's a description of how the communication would work, and another is the instance of this particular communication. So protocols, we have like world state synchronization, a protocol on how you join a game, whereas an API would be the specific calls for join game. The protocol would be what order those things happen in.
And what the network would be words?
So the network, it would be words. What do you mean? So
If you're
so my audio channel. Yes. Yeah. My network is audio network. I'm using a physical sound-based communication network where I emit phonemes from my mouth, and they travel through the medium of the ear, and your network receiver, your sockets are your ears, and you open your sockets to listen to me, and you open an output socket that is your mouth, and you communicate through the air medium. Yes, that would be right, and the protocol would be that I speak, then you speak, then I speak, and the interface would be the English words that we use. Yes, that would be how you describe that. Though I've not described your ears, though, yes, your ears are all sockets, but you're apparently not supposed to put anything larger than your elbow in your ear, so if you listen to your mum. Okay, so 0MQ is another library. It's another relatively lightweight, very fast. It's a C library, right? So it doesn't use the classes in C++, but it uses a low-level C library, so it kind of is optimized. So it is a concurrent programming framework as well, so you can do things in kind of, multi-threaded open environment where you don't know when things are going to happen. So if we look at simple network patterns, so we have a request and reply. So I had a server that was just listening to my client, right? It wasn't sending anything back to the client, it was just listening to the client. When the client said something, it would print it out on my screen, right? So that was a simple just listening. Here is a server that when it has something in, it then replies. Right? Now, with my client, I can actually hit up my server to talk to port 80, and the client would send something, then go into listening mode to see what came back. Right? So send, and then listen, send, and then listen. And the server would be listen, then send, listen, then send. Okay. So in 0NQ, you can have the server set up like this. So here I have again, you can see this socket opening up activity. So here is a socket T, socket context, and 0MQ rep, which is a representation of the context. And this is port 555, and this is a TCP open socket. And I'm waiting on the request, and so here is a receive request. The RECV is the socket receive, and I print out hello world. Right? Whenever I receive something, I just print out hello world. I sleep for 1 second, and then I reply by mem copying into my reply data the string world, and then I send reply. Right? So this is you send me anything, and I'll respond with world. Right? Now the client here is saying, okay, I'm a client, so I will connect to Hello World server, which is localhost 5555. That was the 127.0.0.1. And in here it does the set up a for loop where it goes through and sets up the request buffer and goes through and sends a message with the word hello. It prints out that I'm writing a hello and the message I'm sending, and then it sends that request, and then it gets the reply, so it goes to message reply, socket receive reply, and then prints out receiving world. Actually, neither of these two programs actually know whether they got hello and world at all, right? They're not printing out what they receive or what they get. They're just going, oh, I got something, print out I received hello. And here I got, oh, I got something, print out world. Right? So this is actually cheating. It is not actually sending those. No, it's sending those data. It's just not using that at all. Right? But it's just a way of saying I got something and I got something back. So we have more. Yep. So in 0MQ, that is a blocking receive call. Right? So different libraries will do either blocking or non-blocking, and that is also in the configuration of your socket, whether you have your socket as being blocking or non-blocking. If you have a blocking call, the program will just sit there and wait and do nothing, right? Which is terrible if you're in a game and that's in your main loop, right? Because you're just stuck and waiting for the server to tell you something before you continue. That would be really, really bad, right? And so usually throw that off in a separate thread. So blocking calls go on their separate thread, and they run in the network thread, and so they block, waiting for something to receive, and then the rest of the program keeps running. And when they receive something, it wakes up the network thread, goes, I've received something, processes it, and uses a shared data to communicate into the main thread. Right? So usually you have blocking calls on separate threads. If you're going to have it in the main loop, you have a non-blocking call, which says, do you have anything right now? And if it has something, it gives it to you. If it doesn't have anything, you move on. And then the network card actually has a buffer where it stores information. So some network patterns, and I make sure I don't go too long because we've got people in here at 2. So publish and subscribe. So here I have a server who's going to publish data. So like when you guys connect to a cloud server, you've got a server that you're going to bind to, and it will send you updates, right? So here I have a subscriber, and it connects to a publisher, and I connect it and just sends out data. So for example, you guys are fascinated by the weather, it would seem, in Norway, right? You discuss the weather a lot because you seem to have a lot of it. You know, in countries where they don't have so much weather, they just don't talk about the weather because it's always the same. But in Norway, it's a bit variable. So we could have a weather service, which you, as a client, you don't send information to the weather service. Right? You're just saying, what's the weather in my town? So you ask it for, you send the information you send it is, hey, I'm interested in my town. And then you listen to that data coming out, right? And so here I could set up this would set up a inter-process communication, an ICP bind on weather with a TCP port, and here I can set up the sending of information. So this is something that will broadcast information out to anybody who happens to be listening with zip code, temperature, and relative humidity. At the bottom there, you can see, and it does publisher.send message. Right, and so anybody who is this connected to TCP port 5556 or the ICP port, weather.icp local, will receive that message. And so as a client, you then, oh, okay, I'm going to grab that message, and I'm a subscriber to the socket in here, and with that subscription, I then go down and find, oh, what actual piece of information I'm interested in. Right, so I just connect to that socket and listen to that socket. Anytime that socket sends me something, I go, ah, right, is that useful for me? Shall I display it to you? Right, so it listens to the socket, and you see this bit here, filter. So this line filter right in the middle here. So const char filter equals argc1 argv1 1001. The subscriber set socket option. So 0mq subscribe filter string length filter. So it actually sets up a filter to only listen to the one you want to listen to. Right. So that was the zip code. So in this case, 1001 or 10,001 was the New York zip code. So UAVIC would be 2815, and that would give you the weather. You'd limit it to just your weather, right? Because you'd have filtered all the packets. So the packets come to your computer, you then throw away all the packets that aren't for you, and you only listen to the ones that you want. So network patterns. So there's asynchronous client server. So client connects to the server and sends a request, and then for each request, the server sends 0 or more replies. The client can send multiple requests without waiting for a reply. So you as a client can ask me lots of questions, and eventually I'll get around to answering them all. Servers can can send multiple replies without waiting for a new request. Right. So here, this is completely asynchronous. You can send me stuff. I can send you things. We have 2 open sockets usually, and we're just talking back and forth to each other. Right. Now, one of the easiest ways of setting this up is actually you have a listening socket and I have a listening socket, and so you send to my listening socket and I send to your listening socket. So we're not using one socket, we're actually using 2 sockets, and so we have threads listening and sending all synchronously or asynchronously all the time, right? So I send some stuff, you send some stuff, I send some stuff, you send some stuff, right? So this is the asynchronous server pattern, right? So it's not I send stuff, wait for you to send something back to me. Right? So it's not like walkie-talkies, right? You guys know when you guys as kids, do you get walkie-talkies? And you have to talk, and then you have to say over, and then press you hold the button down and you talk, and then say over and you release the button, and then it goes all staticky, and the other person presses their button and can talk to you, right? Because you can't both have your buttons down and talking to each other because it's got to be synchronous. Right? So that's a client-server model where it's synchronous. I send and then wait for a reply, and then once the reply is over, I can then send. Right? Now you saying talking on the walkie-talkie, saying, "Are you there?" Over. Over tells you it's basically the /0 of verbal communication. It's the null terminating string. Right? That's what the word over is supposed to be. It's supposed to be null terminating. Doesn't always work that way, but it's the goal. So you can have network patterns which are parallel patterns. So if I'm sending some results to you, I can actually send a network. I can send it out multiple ways. They can process and adapt it, and then get it all back together and send it to you. Right? So sometimes you'll actually have, particularly in cloud systems, a piece of data might actually come from multiple sources, and so when I'm wanting to try and get data, I don't just grab it from one server. I'm actually grabbing it from 5 or 6 servers that all integrate it together and give it to me. Right? So I connect to this sink here, and it actually collects a lot of information from a lot of places. Right? So it's not a simple direct connection. Network queuing. So if I have 3 of you guys wanting requests, right, so you've got 3 questions to ask me. When I get that information, how do I queue the network packets that are coming in? How do I order them? How do I give service to different clients. One simple way is to say, if you've got 3 questions, I'll answer 1 question from you, 1 question from you, and 1 question from you. And they'll come back to you and say, what's your next question? Right? And then you don't have another question, and you have another question. Right? And then I'll come back to you and say, what's your 3rd question? So that's what I've got there, right? I asked first question, you got the 2nd question, you got the 3rd question, you got the 4th question, the 5th question, and the 6th question, right? Because I was trying to give 1 packet each, right? That's one way of doing queuing. Because if you and I are talking and you keep asking more questions, you two get what's called starvation, right? You sit there wanting to ask the server something, and the server's too busy talking here to listen to you guys at all, right? And you may have had this when you're trying to connect to a game and the server seems down, and yet someone's got good connection to it, right? Because it's not doing fair queuing of data packets. You can also have this problem with ping time. So sometimes if it's got high ping, if you prioritize high ping, it means that I go back and forth with you constantly, and they're so slow that I'm going to ignore them. So yeah, you've got to understand how those network packets are coming in.
A system like this is more vulnerable to DDoS attacks, right?
Yes. Yep. So how you deal with queuing, how you deal with DDoS. So networks dealing with denial of service attacks. There are various approaches. One is to block all traffic from particular IP chunks, and so you just block everything. But so actually one of the things they're terrified of is that because there are so many unpatched machines in like the US and in Norway, you can build bot networks of people's home PCs. And then you can do a denial of service attack, and it's very hard to tell that it's a denial of service attack because it's coming from within the country.
There's also found a bunch of apps in the App Store that have botnets.
Yes, and then they attack from wherever your phone happens to be, and if that's in country, it makes it nearly impossible to stop. So botnets also have this load balancing. You need a router to do load balancing, right? Say, okay, well, where are these questions coming in? And you have a bunch of cloud servers at the bottom here, and you have some proxy server that has a router and a proxy and another router. So it appears to you guys as a single service, right? So the Amazon Web Service, single place you come in. It actually has thousands of actual physical servers that are serving your requests, right? So this is a standard load balancing broker system, right? Where it tries to use the servers it has available to give you a response, right? And it routes those things, which if you have one point of contact means you do a DDoS on that central router, and yes, everything slows down. So sometimes the Windows Update had that problem. They had a centralized point, so they had to actually change where the Windows Update server was because it was taken down by DDoS. So yeah, so you got challenges when you have a single one. If you want to look at more network patterns, the 0MQ guide, so zguide on 0mq.org, shows you lots of different network patterns and how they work and how you can communicate through them. We mentioned multi-threading. So if you have a look at data structures, if you have a look in here, this bit of while true and blocking requests, you don't want to have in your main loop, right? And so you actually want multi-threaded data structures in here, and you want to set this up using a threading tool, right? So that bit of code is a problem if you had it in your main loop, so that's going to be thrown off onto a thread. So data structures, you guys know about queues? You did queues you're doing the algorithms course at the moment?
Yep.
But you did queues in the previous year, so you know about a queue. You know nice linked lists.
Yep.
So queues are very important for data structures, for networking, because your messages come in a queue, right? They put in and you put them on the network card. The NIC card has memory, that's a queue. Right, so data's coming in and you've got to pop it off. If you wait too long, you lose it, right? Because it fills up the queue and it's got no memory left, so your NIC card just stops dropping packets. Right, so if you've got network packets coming in, you better go and deal with them. You can have linked lists, which are also very useful. You guys know enough about pointers and linked lists? You've
Yes.
done all that? That's all good. So network packets, if you're throwing them around memory, sometimes you have to throw them around as lit mists. Circular queues, you guys covered circular queues? A little bit. So circular queues are also quite useful. You have a read position and a write position, and then as you get to the end, you move back to the beginning and start overwriting that material. Right? So you have a write head, which is writing your data, and a read head that's reading off data, and then when you get the write head gets to there, it jumps back to the beginning and starts overwriting the data you've used. This should block once your read head hits your write head. So at that point it can't write, it has, well, yes, when the write head has got a head of the read head and hits the back of the read head, I haven't read this data and you want to overwrite it. And at that point I go, sorry, buffer full, buffer overload. And I just start rejecting packets. Right? So circular queues are usually the way that data is stored. We do some game instances of networking because games push networks harder than most networking protocols. So most of the stuff you guys do, you won't actually require high-speed network if you're just doing chat, right? If I just send chat, I don't need high-speed network. If you're sending files, you use TCP IP because you don't want to use UDP and have it ultra fast. You just want to get it there in its entirety in one go, right? And so you use TCP, you send the whole thing in one go, right? And you don't really care how long it takes. Most of the networking you do, actually, you guys probably watch a lot of YouTube and streaming videos.
Yep.
So, yep, they have to worry about with, like, do you want your network to give you a perfectly smooth video, or do you want it to give you the most up-to-date video? So what do you do when you lose data on your Twitch stream? What do you want to happen? Do you want it to stop and wait and buffer and then start playing smoothly? You might want it to skip ahead, right? So if you're using TCP IP, for streaming data, as soon as it got something it didn't know, it would stop and wait until it had got that before it start playing again, right? And it could buffer all the ones in front, but it would have that window where it just wait to fill up. That might be bad if you're wanting a live scoring, where every time it drops a packet, it waits 5 minutes until it's got the packet again. You might want it to just drop that and start playing the most recent packet you have. But you probably want a wee bit of a window on that. So game updates, we've got synchronous games and asynchronous games. So if you're playing chess by email, you probably don't care about the speed at which the email gets sent, right? Because it's very asynchronous and it's okay. I can wait an extra millisecond for my chess move to arrive. If you're playing a first-person shooter game and you press fire and the guy was there and then it lags and they're not there anymore because your data was out by several frames, that's a problem, right? So games will often, for synchronous games, use UDP and a much low level, not have that TCP, like go back, wait, send an acknowledgement, wait until I get the new packet back, and then start showing you what happened. It will just get whatever data packet it can, the most recent version of the world is the true version of the world, and just update that way. So you get a client server. Most of you will have played on client server systems, where you have a server, it has the ground truth of the world, and you have, as clients, all look at that server. Right? So with this, you usually have a dedicated server, and it's listening, and sometimes you can have a migrating server where you have a server that is listening, but you have one of the clients is a backup server, and so what happens is, as a backup server, I'm listed on all the other clients as the next person you go to if you can't connect to the server. And so the server is sending me additional information so I can take over in case the server goes down. And then if the server goes down, you migrate to the next client that was the possible server. Right? This requires quite a lot of coding from you as a game developer, And so a lot of games don't do this. If the server goes down, I think you've played games where the server goes down and everybody stops. Yep, that's the standard way you do this, because that's easy, right? Because you just said the server is in charge of everything. Migrating servers, because a secondary machine is set up as someone who could take over the game if the server goes down. The server goes down and you ping it, the game pauses for a second while everybody's pinging the server that is now dead until they go, okay, I'll look at the next server, it's that one. Bang, and they all shift over to the secondary server, and then that takes over as a server, opens up the port, starts listening to the clients, and starts running the game from that one. Right? That gives you a much more stable game, so when the server crashes, your game can continue. But most games don't do that because you guys don't actually pay for stability, and servers don't crash that often, so we don't need it. You've a peer-to-peer. Instead of going through a centralized server where I know your IP address and I send it to you and then you send it to everybody, I need to know the address of every person in the group and I send it directly to them as well as to you. So in that case, it's easy if everybody's on a public network. It's harder when some of you are behind firewalls. Right? And so one of the things we're going to look at tomorrow, and one of the things we're going to talk about, is how do you punch through firewalls? How do you deal with people being behind a firewall? And private networks and public networks. Because if you're on the same network hub, you usually can find each other. But as soon as you try and find somebody on campus and find this machine from your home machine, you're not going to find my IP address. Right? Do you know why you're not going to find my IP address of this machine? You'll find the external IP to the EduRoam router, and actually the EduRoam router for the cable is different to the wireless, right? So you guys aren't actually on the same LAN when you're on the wireless and when you're on the cable. Those are different networks, and they've actually locked down ports communicating between them. So unless they open up a port for you, they won't let you communicate between those two networks. So within the network, if you're all on wireless, you'll be able to do some network communication and find each other's IP. And if you're all on cable, you'll be able to. But if some of you on cable, some of you on wireless, you won't be able to communicate. And we'll also look at how you deal with time when you get old packets. What do you do when you get this round trip time to the server and you're getting ahead of the server? Like, how do I deal with the fact that my time is ahead of the server time? Right? Which, well, because the server time, I'm simulating, and so I'm ahead of the server. Because I've sent a package saying, I've just done this to the server, and I'm now ahead of that. So I'm in the future and the server's in the past. But you're even further in the past. So I've told you that I've done something, and the message is on the way to you, and once you get it, you process it, and then you send it over to him. And so you're two pings in the past.
And then you get shot behind the wall.
And then you get shot when you're behind a wall. And so what we'll do is we'll take this up tomorrow and we'll talk about world state. I'll let you guys go and I'll go and talk to the third years. Tomorrow we'll also do some networking code, and you can play with my code and see what we can set up networks for.
Will the next assignment be in SFML or another Go?
No, we'll be doing stuff in Go still, but I thought it should be useful to show you C++ and SFML if you want to do C++ networking. Right, so this could be useful directly to you. You will probably deal with Indians at some point. You'll pack data, it'll come out weird, and you'll go, ah, why is my data weird? It happens, and it's frustrating. But yeah, either SFML or STL both do similar jobs, but you still have to understand the way in which you're packing data. I was going to show, and I'll do this tomorrow, I do have code for doing this pull high score request, so you can write. So one of the nice things is that we'll show tomorrow, and we can do code, is TCP is this HTTP protocol is over TCP, so I can open up a TCP product, TCP socket, and talk to web pages. and get the data just as strings back from the web page, because it's just data, right? It's just on port 80. And here you can see me getting back from my high score server the HTTP 1.1 200 OK, the date, the server ID, the PHP page version, the content link, the connection is now closed, and the content type, and then it sends me content. And because this is an open buffer that I've just copied into, it's got a whole bunch of junk in the rest of the string because I've just printed whatever I had in the array. And then these are the actual list of items that I got and processed, right? So this is, and if you have a look at this particular request is actually on, if I go to here, oh, don't close it, yeah. So I get that, if I go to the web page, that's what I see. But actually, I get all that header information as well. Right? So yeah, but it means you can start coding directly to scrape web pages with your network. Because it's just data, right? You just request data, it sends you a string back, and you process it and analyze it. And so.
But if you have like zero strings, zero templates and strings, can you have things afterwards? Or would they just ignore everything afterwards?
So you tell it how big the data is. So you can send null terminated strings, because it's not just sending strings, it's just sending data. And so you explicitly tell it how big the data is. Right? Because that's the problem with null termination. I couldn't send you 0 as a number if it was all just null terminated strings. So it just says, okay, I'm sending you 128 bytes of data, which has a bunch of zeros in it and a bunch of numbers in it. Because it's just that much data. You deal with it any way you like. Yep. So. Okay, so I'll go to OBS and bye bye guys.